Hi there, welcome to this, which is video 3 on modelling. We're looking at units and forces. I'm going to start by looking at the unit system that we use, and that system is the SI base units. Now, the SI base units, there are 7 in total. We're interested primarily in these first 3. Now, those are time that we measure in seconds, mass that we measure in kilograms, and length or distance that we measure in meters. The other 4 on our list here we'll look at or use in other subjects or other sciences. So we've got amperes or amps for current, Kelvin, which measures temperature, candela, which is a measure of luminosity or light intensity, and moles, which most of you will have come across in chemistry. Now, this SI base unit system, which will, as you say, will focus primarily on these first 3, can also be used to kind of construct and will define all other units. Okay, so every unit will be made up of a mix of those 7 units. So, for example, a very simple one, we've got speed, which is distance divided by time. Now that means that it's meters divided by seconds, and so my definition, my unit of speed or velocity is meters per second. A slightly more complicated example would be using Newton's second law of force equals mass times acceleration. So I know that newtons, which is my unit for force, is a compound unit of kilograms and meters per second squared, which are my units for mass and acceleration respectively. So force is measured in kilograms meters per second squared, and so 1 newton is 1 kilogram per kilogram meters per second squared. Now, that means that that's an example really of how I can construct or define all other units using SI base units. I'm also going to need to be able to convert units into SI base units if they're not already given to me in that. So, for example, if I have 1.8 kilometers per hour. Now clearly this isn't in SI base units, I need it in meters per second if it were to be. And so I want to think about changing one of these 2 at a time. That's going to be my process, my methodology here. So I'm going to start changing the hours, the time first. I'm going to go, right, let's deal with the hours. 1 hour is 60 minutes, so I can then find it in seconds. So 1 hour is 3,600 seconds. So if 1 hour is 3,600 seconds, and I travel 1.8 kilometers in 1 hour, then I know that this number needs to get smaller if I'm going to put this into kilometers per second as an intermediate step. So I'm going to divide it by 3,600. That means I have 0.0005 kilometers per second. Now, I know that 1 kilometer is 1,000 meters, and so if I travel this many kilometers in every second, I travel 0.5 meters in every second. Okay, so this was a multiplication to get it into meters per second. Now, I would always work it through like this, changing 1 unit at a time to avoid a situation where you're multiplying or dividing incorrectly. I'd always say that you can use a bit of logic here and think about what your unit is telling you to allow you to get the correct answer. So we'll look at one more example. This example is a density unit in grams per centimetre cubed. I've got 12 grams per centimetre cubed. Now, I know that 1,000 grams is 1 kilogram. So let's think about if I've got 12 grams per centimetre cubed of volume, that means I must have 0.012 kilograms per centimetre cubed of volume. So I've divided this by 1,000 to get my kilograms per centimetre cubed. If I multiplied this by 1,000, I'm going to end up with a really, really big kilograms per centimetre cubed, which doesn't quite make sense in the context. So that sense check is a really sensible one at every time. So 0.012 kilograms per centimetre cubed. Now I need to deal with my centimetres cubed. I've got 100 centimetres in every metre, and I've got 1 million centimetres cubed in every metre cubed, so I've cubed both sides here. If I have 0.012 kilograms in every single centimetre cubed of volume of this object or this substance, I need to multiply this by 1 million to get how many kilograms are going to be in 1 metre cubed. Okay, so if I have 1 million of these centimetres cubed in every metre cubed, I've also got 1 million of this amount of kilograms in my metres cubed. So I'm going to multiply for that last step. So that's our units. We've used SI base units, and we need to be able to convert throughout. We also need to be able to identify different types of forces. I have 3 in this table. I've got 7 different forces, and I've got 3 key types. I'm going to ask you to pause the video now and make some notes of this. Please do keep them in the same kind of order, and you may want to leave a bit of space to add anything to each of them. We're going to go through each of the 3 groups in turn in a second. So please do pause and make any notes you'd like to. So our first group of forces are those that will most often cause motion. Now, I've grouped these together because these are the forces that operate kind of primarily externally on objects, and they will potentially cause motion, or would cause motion if maybe we remove other resistive forces. Okay, so these forces are done to a body as opposed to being a fact of the situation, and that distinction will become clearer as we go through. So the first one I've got is weight. Now, weight is a force caused by the mass of an object as it interacts with the gravitational field of another object. Now, that means that weight is what we would quite often call gravity. Now, more appropriately, it would be the gravitational pull. So the weight that's operating on this skydiver is caused by the mass of this skydiver, and it's the gravitational pull of the Earth on that mass. Now, we always, as we've mentioned, kind of want to simplify a model, and I don't want to have to draw this gentleman every single time I'm talking about a skydiver. So actually, I'm going to represent him as just one square, or one kind of dot would be acceptable, with an arrow downwards for the weight. Now, we call this a free body force diagram. Okay, I have a simplified idea of what this object is, and I have an arrow which represents the force, the weight, going downwards. Our second of our kind of key forces in this kind of category, those that are external operating bodies, is the tension. So this example, although not actually one causing motion, does demonstrate it nicely. So we've got a ceiling light. Now let's look at a slightly simpler model where I've got this ceiling light. I've got a tension in the cable upwards, which is holding this light on the ceiling and is counteracting the weight of that light. So the tension is going upwards there on the ceiling light and holds it up to the ceiling. Now you'll notice that I'm interested not on anything to do with the ceiling, I'm interested on the forces that are operating on the light itself. Okay, so there may well be forces up at the top where the ceiling is. I was only interested in the forces that are operating on the light itself. The third of ours is shoveling snow. So we've got compression here, and the example I've got is shoveling snow. Now I'll have some compressive force in this rod here, or in the handle of the shovel, operating on the shovel head, that looks a little like this if drawn using a free body force diagram. So I have a compressive force here on the head of this, on the head of the shovel, pushing it along as I shovel the snow. Now, those three different forces, we say, will most often be those that are causing motion in the problems we look at. They're also slightly different from the other two types of forces we've got, and I'm going to talk about a little bit why that is now. The second group I've got are what we're going to call the contact forces. These are those that are labelled a bit yellow on the original slide. The contact forces, as the name would suggest, exist when an object is in contact with another object. Now, there's two key types. The first would be the normal reaction force. Okay, the normal reaction force, for example, a book on the table, and that might look a little like this. Now, I've got some book, which I've represented as before with just a quick square. I have a weight of the book that's going downwards, and I have a normal reaction force. We're going to label this as R for reaction force, and the normal reaction force points directly upwards and counteracts this weight. If I lift this book or move this table, this contact force disappears, so it only exists if the book is in contact with the table. It's not a fundamental property of this book, like the weight is. It exists as a reaction to the contact. Okay, so this contact force operates as a reaction to that contact. Now, it's really important as well to note that this force is operating at right angles to the contact. So for instance, on this example where I've got a sloped table, actually this book, the reaction force is pushing at an angle, but it is at 90 degrees to the table or where the contact is happening. Okay, the last of my contact forces, or the second of my contact forces, is buoyancy. Now buoyancy, for instance, a boat on the lake, could look a little like this. A very similar diagram. If I have a lake here and I have a boat on that lake, there is a weight going downwards, but there is a buoyancy pushing upwards. Again, that buoyancy will disappear once that boat is no longer in contact with the lake. So the buoyancy again is a contact force. It is a result of the contact between this boat and this lake. Now, I've got one more type of force to be looking at, and that is those resistive forces, or forces that are resisting against motion, and there's two key types here. I've got air resistance, so again, we'll look at this skydiver jumping from a plane. If I have the weight downwards, that body, the person jumping from a plane, will actually feel some resistance on them, and that is caused by the air resistance. Okay, now if the skydiver, for whatever reason, or didn't jump or stopped moving suddenly, the air resistance would disappear. Okay, there is no air resistance if you are not moving. So air resistance is a result of motion. So we're not going to talk about air resistance unless we have some motion through air. The other key type we'll talk about is friction. So again, this resists motion, and again we're going to look at a previous example. So if I look at this example of shoveling snow, if I have a compressive force here which is pushing this shovel along the ground to shovel the snow, I'm going to have some friction which opposes that motion. Okay, so a frictional force which goes against the motion. Now, the friction again will not exist. There will not be a force of friction, although there may well be an ability for it to exist. There will not be a force of friction unless there is some motion. So it's really important to be aware that both of these resistive forces are reactions against motion. These are forces that try and resist motion. Last thing to do is just to try the pre-quiz for me, please. Once you've done that, please do have a look at the sheet and get started. Any questions as ever, let us know.